So there were a bunch of things that we talked about this year, and again, I just want to get you thinking about everything, so we're going to kind of talk about one thing at a time. One of the very, very, very first things that we talked about, or one of the most important formulas that you need to know, is your slope formula. Does anybody remember what the slope formula is? So you have 2 points. You need to find the slope between the 2 points. What are you going to do? So if you don't know, where could you look? You could look in your notes. We don't really have time to be taking through notes for forever. So what's the letter that we use for slope as like the placeholder? M. So remember, it's M equals y minus y over what? X minus x. Good. So again, that's your slope formula. So if you're given 2 points, you have to find the slope between them. That's what you would do. You may hear it called rate of change, or they may ask for a rate of change. It means the same thing. So if they said, like they gave you a table and they said, what's the rate of change from t equals 3 to t equals 5? You would like look at that table where t equals 3, where t equals 5. Use those ordered pairs, plug into your formula y minus y over x minus x. Does that make sense? All right, if you're looking at a graph, how do you count slope? Something over something. Rise over run. So just remember that as well. Rise over run. Rise over run. And then again, like I was saying, if you're given a table, I want to show you what I mean with that. So I said 3 and 5. Give me a number for y. What do y'all want to use? 2 and give me another number. What? 6? Cool. So, like I said before, just to like give you a visual, if they said find the rate of change between 3 and 5, you would do your slope formula with these 2 points. So we would say like 6 minus 2 over 5 minus 3. That's it. Does that make sense? It's just slope. That's something that you've done before a bajillion times. They're just asking you in a different way now. Okay? You all right? Okay, cool. So, the next thing that I want to talk about, there's like 3 big function families that we have in Math 1. So they're linear functions, quadratic functions, and exponential functions. So the next one that I'm going to talk about is linear functions, because that kind of goes with slope, right? So when we're talking about linear functions or linear equations, that's generally slope-intercept form. And we just talked about that in the bell ringer. What is slope-intercept form? Y equals mx plus b. What does that m represent? Your slope. What does that b represent? Your y-intercept. And I want to just remind you of this. The y-intercept is when x is 0. So I put the ordered pair like 0, comma b, because as long as x is 0, that y value is your y-intercept or your b value. You okay with that? All right, so when we were talking about lines, we learned how to graph them. We just reviewed how to do that in the bell ringer a little bit. So remember, you start at that y-intercept, and that's going to be on the y-axis. Then you count your slope. So again, like rise over run, whatever you need to do there. We also talked about like parallel lines and perpendicular lines. So let's jot down some notes about those really, really quickly. Anytime you see or hear parallel or perpendicular lines, what are you thinking of? What's the only thing that we've talked about with parallel and perpendicular lines? They're what? They're slope, right? So parallel lines have what kind of slopes? Same slopes. Then for perpendicular, What kind of slopes do they have? 2 words, kind of big.
Different?
They are different. Do you remember how to like make it different? Opposite reciprocal. So again, the opposite tells us to change the sign. The reciprocal tells you to flip it. Y'all got it? So let's write that down. We'll say opposite, reciprocal, and that means to change the sign and flip. I'm gonna write that down over here. So I'm going to say it one more time. Anytime they mention parallel or perpendicular, what are you automatically thinking? Slope. Yes? So anytime you see parallel or perpendicular anything, you know you're going to be looking for the slopes. Then we also talked about line of best fit. Do y'all remember doing line of best fit? Kinda. So like we were given a table of data, and we entered the table into Desmos, and then we typed in y equals mx plus b, and it gave us the equation that fit that. So I want to jot down how we did that really quickly. So line of best fit here. So for those problems, you were given a table. Odds are, if you're given a table, you probably need to find linear regression or your line of best fit. I do want to jot down linear regression because you may see that terminology. So your steps for that in Desmos, can we like walk through Desmos so that we remember how to do it? What's the first thing? How do you get like a table in Desmos? Hit the plus, the table, so I'm going to write plus, table, and then enter data. So we hit plus, we type in the table, we enter the data, and then we go to a new line. Do y'all remember what we have to write so that it pulls all the stuff that we need? Y1, instead of an equals, what do we put? That little squiggle. Then what? X1 plus B. Good. So we have to say Y1 and X1 so that it pulls the data from the table that we entered. The M and the B, it'll give you those values once you type it in. And then you have your linear regression model. So these two things right here, pretty easy. Those are your steps in Desmos. Are we okay with all that? Does it like come back to us now that we're talking about everything? Yeah? Do we have questions? All right. Is there anything else you can think of that we talked about for linear functions? So are we okay to move on? All right. So the next type of functions that we talked about were quadratic functions. That's where we're going next. So when we're talking about quadratic functions, we need to write down our standard form, and then there's a ton of stuff that we're going to talk about with those as well. So do you recall your standard form for quadratic functions? That's right. So it's a big one. We've got y equals ax squared plus bx plus c. Okay with all that? Is that like familiar now that we've talked about it? Remember those a, b, and c values are the numbers in front of x squared, x, or just your constant by itself. The c value, what does that tell you? Do you remember, did we talk about that a lot? I don't remember if we did or not. That C value is always your y-intercept. Okay? So just like it is with your linear function, that constant is the y-intercept. That constant is still your y-intercept. So again, I'm going to put that ordered pair 0, comma, b. If the A value is positive, what's our graph going to look like? Do you remember? What does the graph look like in general for quadratics? Remember the shape? What's it called? A parabola. So it can be like that U shape or that N shape if it opens down. So again, you've got like that U shape or that N shape, just depending on that A value. If it opens up, that means that the A value is positive. So I'm going to write like a positive AX squared. If it opens down, that A value is negative. So I'm going to write negative AX squared. So it's pretty likely that you're going to have a question where they give you a quadratic function and you have to find the graph that matches it. Okay? You'll probably see it on the inactive part of the test. So you have to be able to look at a function and tell which graph it goes with. So if your function is negative x squared plus 2x plus 4, if it's got a negative out front, you know the graph has to open which direction? Down. So anything that opens up, go ahead and eliminate it. Does that make sense? So you've got to know these things without your graph or without your calculator. If it opens up, the lowest point, what do we call it? Your minimum, yeah? So this lowest point down here would be a minimum. If it opens up, or I said that backwards, didn't I? I was saying if it opens down, I'm pointing to the one that opens up. If it opens up, it's got a minimum. If it opens down, that highest point would be what? The maximum. Do you remember another word for those highest or lowest points that could be talking about either one? Starts with a V. The vertex. So there's a formula that helps you find that vertex. And we talked about it a lot when we were in this unit, but I know it's been a long time since we were there. So the formula to help you find the vertex is x equals negative b over 2a. Is that familiar now that we've said it? Okay, so again, that vertex is your turning point. So that formula just gives you the x value. So if you have the x value, to get the y value, you plug it back into your original function, and that would tell you exactly where that point happens. So again, that might be something that you would have to do without a calculator. Okay, on the inactive section, I would not be surprised at all if you're asked to find the vertex. So what I want to do next is just kind of work through an example. So I'm going to give you a function. We're going to find the roots. We're going to find distance between the zeros, and then we're going to sketch a graph of it. So all things that you may be asked to do without a calculator. So our example is going to be this one right here. So go ahead and jot this down. We'll say y equals x squared plus 2x minus 24. So I have mentioned that I want you to find the roots. What are other words that they may use instead of roots? Zeros? What else? Starts with an S? It's not the problem, but the solutions. And then the last one, they're not the y-intercepts, but the x-intercepts. So if you're asked to find roots, zeros, solutions, x-intercepts, any of that, they're all talking about the same thing. There's a phrase that they use to like tell you that in word problems. If they ask you when something hits the ground, what are you looking for? Zeros, roots, solutions, x-intercepts, any of those things, yeah? So if you see the phrase hits the ground, you're thinking the same things, okay? We need zeros, roots, solutions, x-intercepts. Anytime you're asked to find any of those things, you've got to factor and solve. That needs to be like an instinct, okay? So like an instinct, if you touch a hot oven, you pull away, it needs to be instinct that if you see any of these words, you're gonna factor and solve, yes? So I want you to jot that down here. So anytime we see any of those words, we need to factor and solve. When I say factor, do you know what I mean? That's like undoing the box, where we would take something that looks like this, we put it in the box, and then we pulled out the factors, the GCFs, and then we're like, oh, this is what it multiplies, what multiplied to get us here. So we're gonna do that with this one, okay? So do we like doing the box? Yeah, to factor. Okay, so let's set that up really quickly over here in the margins. So when we're setting up our box, I'm throwing things around over here. What goes in the top corner? X squared. What goes in our bottom corner? Negative 24. So remember that your diagonals multiply to be the same. So 24 times 1 is just 24. So whatever we have here needs to multiply to 24. But when we combine them, we want to get positive 2. So think about your factors of 24. It's going to multiply to 24, but then combine to be positive 2. Will 12 and 2 work? No, because we can't do 12 plus 2 to get 2, or 12 minus 2 to get 2. So what are other factors of 24? 6 and 4. How do we make 6 and 4 equal 2? 4 minus 6? 6 minus 4. So positive 6x, negative 4x. Does that make sense? Brayden, wake up. Yes, no, maybe? Yes? Okay, are we getting this down? So then you pull your GCFs from your columns and your rows, yes? So looking at your top row, what's the GCF right there? The only thing they have in common? X. Look at your bottom row. What's the only thing that they have in common? Or the only thing they can both be divided by? 6. Look at your first column. What's the only thing in common? X. Your second column, there's 2 things they have in common. I'm sorry? Negative and a 4. They both got a negative, so pull it out. They can both be divided by 4, so pull it out. Is that okay? So what are our factors? X minus 4 and x, what? Plus 6. Perfect. Are we okay with that, y'all?
Yes.
Awesome. So from there, once you've got your factors, remember when we're solving, we set each factor to 0, and then we solve individually from there. So we would say x minus 4 equals 0, and x plus 6 equals 0. Then it's one step to solve both of those, yeah? For the x minus 4, what do we do to get x by itself? I just can't hear you, I'm sorry. Move what? I can't hear you.
I don't know where you moved it. I don't remember.
To get x by itself, what do we need to do? To get x by itself, what do we need to do? Just add 4. That's all. That's just solving equations. We've been doing that forever. So add 4 to each side. X equals what? What's 0 plus 4? 4. Same thing on the other end. We have x plus 6 this time. What do you do to get that x by itself? Subtract 6. So what's 0 minus 6? Negative 6. So x equals negative 6. Those are our roots, our zeros, our solutions, our x-intercepts, and we're done. Is that okay? Do y'all remember how we talked about if you look at your factors, you can basically just change the signs? Yeah. If there's a number in front of the x, you have to divide by that number. So if it was like 2x plus 3, then you would say minus 3 divided by 2, so negative 3 over 2. Does that make sense? We've done those a lot. Hopefully they'll come back to you as we do more later. So again, those are your zeros, your roots, your solutions, or your x-intercepts, okay? So we can sketch a graph of this equation now that we've done everything. So what I want us to do, actually, do we want to do this yet? Let's find the vertex and then we'll sketch our graph because I want to make sure that you can find the vertex. So your formula for that is negative b over 2a. So what's the b value here? 2. So we would say negative 2 over 2 times a. What is the a value here? 1. I'm going to go through that one more time. So we said negative b, so negative, our b value was 2, over 2a, so over 2 times a, our a was 1, so 2 times 1. Does that make sense? Did we follow where that came from? We did a lot of this like in Delta math a long time ago. So 2 times 1 gives us what? Just 2. So negative 2 divided by positive 2, what do we get? Negative 1. So the x value of your vertex is negative 1. That's also the axis of symmetry. Is that ringing a bell? To get the whole ordered pair for your vertex, we plug that negative 1 back into our original function. So I'm plugging in back to our original function. We'd have negative 1 squared plus 2 times negative 1 minus 24. Is that okay? Yes, no, maybe? All right, so negative 1 squared, what do you get? That means negative 1 times negative 1, which is positive 1. Positive 2 times negative 1 gives you negative 2 minus 24. So negative 2 and negative 24 is negative 26. If we have 1 minus 26, that gives you what? 25. Is that okay? So your vertex is going to happen at negative 1, negative 25. Is that okay? All right, we're going to be able to sketch an awesome graph of this because we have so much information now. We've got our vertex, yeah? We have our x-intercepts, our roots, our zeros, our solutions. We also have our y-intercept because the y-intercept is what? Negative 24, just that c value that we talked about here at the beginning, okay? So we're going to sketch a graph. So this is a sketch. So it is by no means like perfect, so don't stress about that. The last thing I want to talk about before we graph it, which direction is it going to open, up or down? It's going to open up. Why? That a value is positive. There's a positive or like no negative sign in front of your x squared, so it's going to open up. All right, so we know that it crosses the x-axis at positive 4 and negative 6 because those are your zeros, your roots, your solutions, your x-intercepts, yes? So I want you to sketch that out. Go positive 4 and put a dot, and then go negative 6. And put a dot. Those are your zeros, your roots, your solutions, your x-intercepts, yeah? The next part's going to be a little bit tricky just because the scale here, but it's not a big deal. Our vertex is at negative 1, negative 25. So I'm going to go negative 1, and then we'll come down as far as we can and make that negative 25. Does that make sense? And then our y-intercept is supposed to be at negative 24 because that's our c value. So it would be just above that. So we'll put it somewhere in there. And then we said it's opening up, so we can go ahead and sketch our graph from here. Again, this is a sketch, so it's not perfect. Mine's kind of ugly, but that's okay. Are we all right with that? So based on the stuff that we found here, you should be able to like match your graph if you had to. Yeah? And ideally, half the answer choices before you do any work, if you just know which direction it's supposed to open, or what your y-intercept is just by looking at it. Does that make sense? Because the y-intercept is really easy to find. Remember, it's just that c value. So if you have a parabola that crosses in the positive section, is there any way that's correct? No, because our y-intercept was negative 24. Is that okay? All right, so we got our little sketch in there. We found the zeros, the roots of solutions, the x-intercepts. We factored, we solved, we got the vertex and the axis of symmetry. Something that I have seen them ask you is for the distance between the zeros, okay? So I want you to jot that down for me really quickly. Distance between zeros. So there's a couple ways that you can do this. We talked about the distance formula last week, whatever it was, right before Christmas when we went home. So your distance formula, remember that's where we did the owl, and you can find how far it is between any 2 points anywhere on a graph. It's really nice about your zeros is that they are directly across from each other, right? So if we have a graph, we can look at it, just count how many blocks are in between. Does that make sense? If you don't have a graph, you could sketch a graph, once you find your zeros like we did. Yeah, as long as you have like a number line, you could count the distance between your zeros, okay? So that's what we're gonna do really quickly with this one. So from -6 to 0, how many blocks did you go? You don't even need to count. 6. From 0 to +4, how many blocks do you go? 4. You don't even need to count. So what was the total distance there? 10. So we had 6 plus 4, which gives you 10. That's your distance between your zeros. Again, there's a couple different ways that you can find that, but I think just looking at the graph or like making a number line is the easiest way to do that. You could do the distance formula if you wanted to. Do you have questions on anything that we've talked about so far? Are we okay? Is this coming back to us? Are we feeling any more confident at all? Yeah? Okay, great. So we will move on to the next topic. So our last function family that we talked about was exponential functions. Do we remember those? Exponential functions. That was more recent for us, so hopefully it's still pretty fresh. So there's two kinds that we have. You've got growth, you have decay. Yeah? What happens with growth? Gets really what? Really big, really fast. Yeah, so when you sketch that graph, which is what we're gonna do here really quickly, it's getting really big, really fast. So we're gonna say really big, really fast. That's what it looks like, yes? Same idea for decay, but instead of getting really big, really fast, what happens? It gets really small, really fast. So it's gonna look more like that. This one's growth. This one is decay. There is a key point that all exponential functions are supposed to have. Do you remember what it is? It's our y-intercept. So we've always supposed to cross at the same place. So that y-intercept is when x equals 0. So anything to the 0 power, do you know what that is? 1, right? So that's always supposed to be the point 0, 1. If it's been moved up or down, that was where that k value came into play. And we talked about that at some point on your test. Yeah, do you remember that? So like if it was moved up a couple blocks, it'd be like +2 for your plus k or whatever. Or moved down a couple blocks, it'd be like -2. So just remember it's supposed to cross at 0, 1. Any different than that is that k value coming into play. What are some words that tell us they're talking about growth instead of decay? Increase. I think that's the biggest one. Instead of increase, what might they say for decay? think like opposite. Instead of increase, we could say decrease. There was a fancy word they used for decay. It was depreciate. Do you remember that? And it means that it's like going down or getting smaller every time. So I'm going to put depreciate. You may hear appreciate instead of depreciate for like increasing. It's very, very rare. I don't know that you'll actually see it in this class. But the kind of like the opposite or pair that goes with that would be talking about like investing money or putting money in the bank and earning interest. Does that make sense? Do we remember those? You're like, oh, I deposit $100, it earns this much interest. So that's always like growing or increasing. So I'm going to put interest down here just to remind us that anytime we're talking about interest, it's going to be growth. So the next thing we're going to do is write our formulas here. So for exponential growth, we have y equals, we always have that a value out front, which is like your starting amount or your initial amount. So like if we invest that $100, then that would be 100. Yeah. Inside the parentheses, we say 1 plus your rate. So 1 plus r. And then our x goes in the exponent. That's what makes it an exponential function. What's the only difference for decay functions? We subtract r instead of adding r. And again, that r is your rate. They're going to give it to you as some percent. So if there's a percent in your problem, odds are that's your rate. So we'd say a, then 1 minus r. And again, it's still to the x. And that x is usually our measure of time, so however many years most of the time. Or days or weeks, just depending on the problem. I want to jot down 2 things at the top of your page. Rate versus factor. Do you remember those things like your growth rate or your growth factor or your decay rate or your decay factor? Do you remember talking about the difference between those two? So the rate is just that R value, just the percent, whatever it may be. What's the factor? Not just the percent, but what? So we do 1 plus the percent or 1 minus the percent. So it's that whole b value, that whole number inside parentheses. So I'm going to write 1 plus the percent or 1 minus the percent, just depending if it's growth or decay. And then I want to do 2 examples just to make sure we remember how. So we'll jot those down next. So, so go ahead and jot down that example really quickly down here. And I'm going to ask you a few questions about it just to like refresh our memory on things. So what would be our initial amount here? That 45,000. Yeah, so maybe we're like buying a car or buying something very expensive. I don't know. So 45,000. That's your initial amount. What would the growth factor be? So look back at the top of your page. Is the factor just the percent or 1 plus the percent? So what would that be here? The 1.04, right? Whatever's inside parentheses, that's your growth factor or your decay factor. So if you want to know the rate, we have to figure out what did they add to 1 to get here. So what did they add to 1 to get to 1.04? What did they add? 0.04. So your rate is 0.04. Convert that to a percent. What would that be? 4%. Do you remember doing that now? So same idea for decay. We're going to do an example for that as well. So go ahead and write this example down on the other side. So what's our initial amount here? Again, that 40,000. What would your decay factor be? 0.87, because remember it's that number inside parentheses or 1 minus your rate, whatever you got when you did that. Then I want to know the decay rate. We need to find that rate. So how could we do that? We need to figure out what did they do. So 1 minus something gave us 0.87. There's a couple options that you could do. You could, I don't know that I would add one. I mean, you could, but then you'd have 1 point something, and that could be a little bit confusing. I usually just do 1 minus that number, and that gives you your percent. Does that make sense? So what is 1 minus 0.87? You could think like 100 minus 87. What do we get? 0.13. Convert that to a percent. What would it be? 13%? Are we okay with that? I didn't mention this, and I want to say it now. If you're just given the function, they don't tell you whether it's growth or decay. How do you tell which is which? So if this number is smaller than 1, it's going to be decay because they did 1 minus something, right? If this number is bigger than 1, it's going to be what? Growth, because they did 1 plus something. Does that make sense? We talked about that before. Again, that's another thing where you may have an example or a problem. They ask you to write the function. That's all you have to do. You'd probably eliminate 2 answer choices because they don't have the appropriate b value. Does that make sense? All right. You may have to run regression in Desmos again, so I want to write down like our general formula for that. So it would be that y1, the squiggle instead of your equal sign, a times b to the x1. And they'll give you those a and b values. So if you had to get a model for a table, that's what you would type in Desmos, like we did for linear regression. But instead of typing y equals mx plus b, that's what you would type instead. Are we okay with all that stuff? Yes, no, maybe? All right. I want to talk about geometry for a second. So that's one of the most recent things that we did. So there were 2 big formulas that we learned at the end of the year. So I want to talk about both of those, and then also your area of a triangle, because that's one that we need to know, but a lot of us tend to forget. So we'll start with that one. What's the area of a triangle? Good. Jot that down just so you have it. I can't spell A-N-G-L-E. Area equals 1/2 base height. Are you good with that? All right, so that's area of a triangle. Then the 2 like new formulas, I guess, that we learned were midpoint and distance. So starting with midpoint, how do you find midpoint? Do you remember? Remember we added the x's, then did what? And then what do you do? Add the y's. Divide by 2. So you're like finding the middle between 2 points, so you're like averaging it. So if that helps to think of it that way, You're adding the x is dividing by 2. Adding the y is dividing by 2. When we do the distance formula, that's where we draw like the owl. So that's telling you how far apart two things are, and we talked about that briefly a second ago when I was talking about the distance between zeros on a quadratic function. So you could use this there, or just between any 2 points. Where I see this most often is they give you 4 ordered pairs, and it makes like a rectangle. They ask you to find the area, the perimeter, or something like that. So you're going to have to plot those points out, find the distance between a couple of them to get all your side lengths, and then do whatever else from there. Does that make sense? So it's not going to be straight up, hey, what's the distance between these 2 points? It's going to ask you to do more than that, all right? So help me set up the owl real quick. We have a big square root, then what? Parentheses to make your eyeballs. What else? We use squares for little eyelashes. What else goes inside the parentheses? Little minus signs for like the slits, because owls have like slitty eyes. And what goes in between? How do we make like the nose there? Plus sign. Is that okay? So then we plug this stuff in. So remember, x's go together in the first step, y's go together in the second step, and then you just type it straight in the calculator. Are we okay with that? Do you remember that? That should be like one of the most fresh things that we've done. Okay. Last 2 things I want to jot down for geometry are x-intercepts and y-intercepts. We talked about it a lot already today, but your x-intercept, we haven't mentioned a whole lot. That's when y is 0, so you would have an x value, the y is going to be 0. The y-intercepts happen when what is 0? When x is 0, so we would have a 0 and then some y value. That would be your y-intercept. So if you're asked to find an x-intercept, you plug in a 0 for y. If you're asked to find a y-intercept, you plug in a 0 for x. Is that okay? This is a little bit, what's up? Yeah, just here. A little bit not really in geometry, but it's important when you know how to do it. We talked about it briefly this morning in the bell ringer when we were talking about graphing inequalities, so I want to jot those rules down really quickly. So if you have y is greater, which way do we shade? Above. If you have y is less, which way do you shade? Below. What's one big rule that you have to remember when you're solving inequalities? We did it in the bell ringer. What do we do?
You're dividing by a negative, you have to flip it.
Exactly. If you divide by a negative, you got to flip the sign. And then the last part you have to worry about is dotted or solid. So if you've got a regular less than or greater than, is that going to be solid or dotted? Dotted line? Or like an open circle if you're just graphing? Dotted, D-O-T-T-E-D. And then if they're equal to, what kind of line is it going to be? Solid or dotted? Solid. Or like you would close in, fill that circle. I want to kind of box this off because it's different. All right. That's all good stuff. Okay, only one more thing that we want to talk about and then we'll be done. So the very last topic that we haven't touched yet would be statistics. Do y'all remember doing statistics stuff? Yeah, I know it's been a minute. It's been a minute since we've done all these things. But you're always doing well at remembering things, so I'm proud of you. The biggest thing first statistics for y'all is box and whisker plots. So I want us to go ahead and draw a box and whisker and then label it with all the things just to refresh our memory, and then we'll talk about a few of the things that you'll be asked to find. So we'll go ahead and draw our little box and whisker. So there's like 5 numbers on a box and whisker, and we call that the 5-number summary. Is that coming back to us a little bit? All right, so tell me about the very, very far end. What do we call that? Like your smallest number. Your what? Your minimum. What else might they call it? Lower, not quartile, but the lower extreme. Not okay? So they kind of, those are interchangeable, so I'm not entirely sure what you'll hear. It kind of just depends. So you may hear both. So it could be the minimum or the lower extreme. What about on the opposite end, all the way at the top? What would this be? Your maximum, or what else might they call it? Your upper extreme. Good. What else do we know? The middle is the median. That's something that we've been finding since like elementary school, right? What's that? Can you do what? Yeah. Do we remember the low edge of the box? That's your lower quartile. Or they might call it Q1. And then what about the upper edge of the box? What would that be? Your upper quartile or Q3. Upper quartile or Q3. Are we okay with all that? All right. Each chunk, do you remember what percentage each section is worth? 25%, because it's split into 4. So that just makes sense, right? 100 split into 4 has got to be 25%. So I want you to jot that down. Each chunk is 25%. I probably spelled chunk wrong, but that's okay. So if I was to ask you, what percent of the data is between the lower extreme and Q1? What would you say? $25%, because there's only one chunk. Yeah? If I were to ask you what percent of the data is between Q1 and Q3, what would you say? 50%, because how many chunks? 2. Does that make sense? If it's asking you what percent of the data is between anything, it's either going to be 0, probably not, 25%, 50%, 75%, or 100%. Right? Those are your only options. It's not going to be any other random number in between. Okay? So that's important to know. You're going to have to compare things. So you'd be looking at more than one and talking about what's higher, what's lower. Do you remember the more spread out it is, that's like a higher variance. The smaller it is the lower variance or standard deviation. Do you remember those things? Yeah. IQR, do you remember how to find that? Q3 minus Q1, perfect. So again, the bigger that number is, the more spread out your data is, the higher the variance, the higher the standard deviation. The smaller that number is, probably going to be like your data is closer together, so your standard deviation and your variance is going to be smaller. To find outliers, first off, do you remember what outliers are?
The numbers that are way too high or way too low.
Exactly, way too high or way too low. There's a formula that helps us find those. Do you recall what that formula is? That's 1.5 times your IQR. Remember we called that the magic number? So we take that magic number, we add it to Q3, that gives us the upper fence. We subtract it from Q1, that gives us a lower fence, and we see if anything falls outside of those boundaries. I want to jot down notes about standard deviation variance really, really quickly, and then we'll be done, okay? So if it's widely spread, or actually, no, hold on, pause. Before we move on from outliers, do you remember what outliers do to your data? They skew it, yeah? So if your outlier is big, it's going to pull everything towards it. It's going to make everything go up. So then when we remove that outlier, things are going to snap down, right? If the outlier is small, it's going to pull everything down, like if you get a 0 on a test. If you remove it, then stuff will go back up towards the center. That's all stuff we've talked about before. And then if you have an outlier, it's going to make your data more spread out. We remove it, the standard deviation, the variance is going to go down, right? So I want to just jot down that if it's widely spread, it's going to have a high standard deviation. Instead of widely spread, if I say like compact, does that make more sense? Because it's like tight or close together. Do you want me to say close together or compact? What makes sense to you? If there's an outlier in the data, the standard deviation is always going to be high because it's different from what else is there, so it automatically pulls it further out. If you remove the outlier, that standard deviation is going to drop every single time. That'll always be true, no matter if the outlier is big or small. That's kind of all we got. Are we all right? How are we feeling? Do you feel like your brain is completely drained? Yes. All right. So we've got like 20 more minutes. We're not going to get through all this stuff for today, which is not a big deal. I'm not super stressed about it. So I just want to go through, we'll look at review day 1, and we'll just do this topic we need to. How's that sound? Yeah, so we'll like read a problem. If you feel like you're good on it, we won't do it. If we read a problem and you have no idea where to start, then we'll do it. How's that sound? Okay? All right. You're going to have homework every night this week. So let me pause